and welcome to Injection Molding, the Whiteboard Sessions. I'm your host, Brandon Birchmeyer, and today's first episode, we're going to be starting the constant pressure molding series. And the first episode of that series is, what is constant pressure molding, i.e. influx? So, brief introduction today around the constant pressure molding philosophy and technology. Let's dive right in. So what I've drawn up here is an injection molding machine. I want to show you kind of how the hardware is interacted and then how the software works on the machine. So the first thing that is done is an adapter is installed between the end cap of your barrel and the nozzle. And inside that adapter is housed a sensor that measures pressure of the plastic melt. So that was where the plastic pressure that is controlled is measured, is in that area. There's a box that houses both hardware and software. And what that does, what that hardware is doing to the machine is it's controlling your injection signal or the voltage being sent to the screw during injection to speed up or slow down the screw relative to a pressure set point that is identified in your HMI. Again, that pressure set point is relative to the sensor that is measuring plastic pressure during injection. So what's happening is the injection profile is being taken over with this technology. Nothing else. You know, your screw recovery, your clamp, everything else remains the same. Only the injection profile is changed on the machine. So to kind of demonstrate the differences, what I have drawn up here is just a simple, rectangular test bar, and to demonstrate what a decoupled, kind of conventional molding process would look like relative to a constant pressure molding process. And I have some injection molding graphs up here. They probably look familiar to you if you've ever used a injection molding machine or some other third-party software like eDart or Influx. So what I'm looking at here is, in the green line is plastic pressure, again that pressure that's measured at the nozzle. Screw position is the blue line, and screw velocity is the purple line in these graphs. So in a decoupled process, right, decoupled meaning we're decoupling the fill portion of the process from the hold portion. So we fill, right, with a velocity, usually a high velocity based on rheology, to 90-95% full of the part. And while we're doing that, what's happening is we're skinning the polymer across the tool steel like I have drawn up here. And then, at that transfer point, right, once we achieve that 95% full, for example, we go into a hold phase to densify, wait for that gate to seal, right? So the polymer is captured and densified inside the tool steel. And as we're doing so, you can see the screw moving in a linear fashion and maintaining a cushion during that whole profile. So that's kind of what a decoupled process would look like on a part like so. The constant pressure process is a bit different, right? Instead of pressure being an output of the process during fill, it is always the input of the process. And there is no transfer. This is all one stage, one movement of the screw. So what happens, interestingly enough, is velocity goes quite high as I'm trying to achieve my pressure set point here. It's a wide open system, for example, right? There's no, initially there's not a lot of pressure buildup, so we're able to generate quite a bit of velocity. However, as soon as pressure is achieved in this instance, what happens is there's a hyperbolic slowing of the injection velocity, a deceleration, if you will. And this deceleration is how kind of two things are happening at once now in this process. It's packing as it fills, as Influx says. And if you were to, again, look at the flow front as it's traveling through the tool, what's happening is there's a much thicker skin layer in this instance, and a much smaller channel of molten material going through. Because we're decelerating, right? We create a lot of shear up front to get the polymer moving and aligned, but then there's a deceleration, so the flow front continues to move forward, but it's also packing that part out as it's moving forward. It's doing two things at once, packing as it fills, like they say. So in a decoupled part, if I didn't have the hold phase, that part would be really shrink away from this frozen layer. A short shot, it has lots of sinks, pitting, things like that. A part made with constant pressure, this part could be about 75% full and be completely packed out. It'd be a pretty packed out part in this instance. It's not going back and trying to fix those things in the hold phase. It's kind of now allowing those sink marks and whatnot to happen as the flow front's moving forward. So there are a few benefits to this process that I'll go over quickly. One is it's 100% feedback based. The mold is dictating this velocity all the time in a constant pressure process. There's just always a feedback mechanism, the mold's geometry being that feedback mechanism. In a conventional process, when you're saying inject that 4 inches a second, that's what the machine's going to do. It's going to inject that 4 inches a second. It's not really paying attention to the mold. In fact, your molding machine doesn't really care what the mold is, right? It's doing what the operator's telling it to do through its own interface. So the mold matters. The mold's always feeding back in this instance. Lower peak pressure requirements. Again, if I'm using high, rheology-based fill speeds, I'm going to generate a bit of pressure as that flow front continues on this part, as you can, as seen here. In a constant pressure process, that peak pressure is going to be about 30 to 50% less than it is in a decoupled process. And that's giving you a few examples, a few benefits, One is residual stress. I want to reference a John Bazzelli article in Plastics Technology from a while ago that mentioned, he had a break on him in his yard, and it probably had gate seal, right? And what's gate seal is doing is trapping a lot of stress around those gate locations in your part. Pressure is not helping that in that instance. You're creating a lot more residual stress around those gate locations in a decoupled process. And there's also less tonnage requirement. Pressure means tonnage, right? You're using tonnage to keep that clamp closed. This pressure is what's trying to open it back up. So less pressure, less tonnage in the process. Elimination of transfer, right? Like I mentioned, it's doing two things at once. It's a very efficient use of the screw. We're packing and filling at the same time. You'll never see a screw bounce or anything like that in a constant pressure process like you may in a decoupled process when you're hitting that transfer at very high pressures, and perhaps you got to get to a very low hold pressure profile. Cycle time savings is seen as well, right? So a decoupled process, you need that hold phase to finish and achieve gate seal. In a constant pressure process, that's all happening at once. So this will take longer to fill your part. However, injection forward time will typically be less. So that's where you'll get your cycle time savings from. And in future videos, I want to cover, how cavity imbalance isn't nearly as sensitive in a constant pressure process. We'll talk about viscosity variation, how that's handled through the auto viscosity adjust technology in the constant pressure process, and then also benefits to sequential valve gate molds. Think large automotive parts and the benefits that can be found there as well. So thank you for joining my first episode of the injection molding whiteboard sessions. Please like and subscribe, and I appreciate your support. Now a word from today's sponsor, myself, Brandon Birchmeyer again, president of Birchmeyer Plastic Solutions. If you're in an injection molding facility, you need some troubleshooting help. You may need in-house training. Maybe you need to help figure out how to add more flexibility or bring recycled resin into your operation. Please reach out. I'd be happy to help you and talk you over with your issues and see if we can provide some support. So thanks again for joining me in my first episode, and have a great day.